All right, everybody, let's get started. It looks like we were able to find some times for a drill that work. So they're up there. They're also posted on today's slides on Blackboard, which are posted right now if you want to follow along. If one of those times does not work for you, let me know right away, because otherwise it will be a bit too late to change things. Also for today's class and through probably Monday or Wednesday of next week, we'll be going through content that's loosely covered in the Judd et al. chapter 8. But with all this needed, as with much of the class, really, I'm drawing from a variety of sources, so the Judd textbook won't match exactly what we're doing, but it covers similar ground and it's written from a similar perspective. So don't expect everything to be reflected exactly, but it still should help to reinforce some of the complement steps. Right, so we have lab times that are posted on Blackboard. We're going through content that's matched by the Judd chapter or loosely matched Judd chapter 8. So for this unit, categorical variables with at least 3 levels, we're going to be considering 3 general cases where you might be using these kinds of variables as a predictor. One case is where you have a planned hypothesis and you're making a custom set of comparisons to test that hypothesis. The second is where you're still in this planned situation, but you're making pairwise comparisons between levels of categorical variable. And the third case is where you're making unpaired comparisons. All this might not make sense right now. I basically want to give you some structure for where we're going. Hopefully it'll make more sense after today's lecture. The general idea is that we'll be working with cases both where you have a planned hypothesis that you're testing, ahead of time before you collect data, and then there's another set of situations where you're working with some sort of unplanned hypothesis source. You might not even be working with a hypothesis at all. Today, we're going to be working with this first situation where you have a particular hypothesis that you're interested in, you have a plan for how to test it, and the specific tool that we're going to cover for this situation is called a set of orthogonal contrasts. This term, again, probably doesn't make much sense to you right now. It's just a bunch of words thrown together. But over the course of the lecture, I'm going to try to hit on each of these different components. And towards the end of the lecture, I'll try to circle back and talk about what exactly this means to have contrasts that are planned and orthogonal. Before we get to the what a planned orthogonal contrast is, I'd like to remind you all of the approach that we took with simpler types of categorical variables. So categorical variables where you're working with a dichotomy. The dichotomy being, male versus female, treatment versus control. It's a variable that you can divide up into 2 different categories, and where the categories are mutually exclusive. You can either be treatment or control, you can't be both. And I'm going to be working with a sketch of a research scenario that's a little bit new. So I'm drawing on the body of research by John Curtin. John Curtin was my instructor for stats. He did alcohol research, and I actually was a pilot subject in some of this research. I got drunk, and and I was exposed to pictures of death and porn, and I had to make gambling decisions in between. I always thought that his lab must have to be interesting parties, but his lab basically does a lot of research where you have people drunk and let's see what happens. And one of the ideas that's come out of his lab, and other people's labs too, is that one of the effects of alcohol on people is to reduce anxiety. Probably makes a lot of intuitive sense if you're a drinker at all. But they have all these different studies testing variations of this idea or how it happens neurobiologically. And so one of the tools that they use is startle response. So basically you blast a bunch of a short burst of white noise at somebody, and it's pretty sudden, and it evokes a startle. And it does so pretty reliably. I won't get into the details of how it works, but basically you can measure people's reactions to trials where you get this burst of white noise and trials where you don't. And that difference in reaction time can be considered a measure of anxiety or fear, depending on the other details of the study. So basically, we're working with a measure of anxiety, and in this first research scenario, we've just got a bunch of people who are asked to drink or not, and they go through a bunch of trials where you measure anxiety. So for this first data set, the hypothesis that we're looking at that the study is designed to test is that alcohol reduces anxiety. So if you have a group of people who that's drunk or not, the drunk group ought to have a lower startle response, lower levels of anxiety. So when we first learned how to analyze this kind of design, where you have a dichotomy and some sort of outcome, I showed you a graph like this. So you've got labels on the bottom, alcohol versus nothing. And the problem, of course, that we looked at the beginning is that these labels are not numbers. And when you're using the GLM, you need to have numbers. You can't have labels. So what's the solution that we used when we first learned how to analyze this kind of design?
And we were talking about the 0, 5, and 0.5.
Absolutely. So you just choose, you can choose pretty arbitrary numbers, actually.
One, like -1.
Yeah. Whatever you want, as long as they're different. So you just choose numbers, whatever numbers you like, and you replace these labels, these text labels, these categories with those numbers. And so what we learned is that certain numbers are a little bit nicer to work with than others. So we use -0.5 and +0.5 a lot. That has some nice features. You ensure that the distance between the two labels is 1. So that means that when you do your regression coefficient will represent the mean difference. And then the intercept will represent the average of the two means. So that's just kind of a nice feature of using -0.5 and +0.5, but you could use others. That would be perfectly fine. And if you used others, your t-statistic, for example, for the test of the mean difference will be the same. So this is the solution that we came up with. You just replace those text labels with arbitrary numbers, and that gives you a variable that works a bit more nicely in the GLM. So going back to the hypothesis that motivated this hypothetical example, so it's that the mean of the alcohol group ought to be lower than the mean of the control group. I just want to point out here that what we're doing is we're creating you can call it a mechanical variable. That's a term that gets thrown around some when dealing with categorical variables. Mechanical variable just means that it's a constructed variable. It's something that you're creating as part of doing whatever hypothesis test you want to do. Another term for this particular kind of mechanical variable is contrast variable. It's called contrast because you're contrasting groups. So mechanical variable is, there are lots of different kinds of mechanical variables. One other mechanical variable that we worked with in the past is to help test interactions. So that product term, that's a mechanical variable. This is another mechanical variable. This particular kind is contrast. And that minus a half and positive a half actually represents the hypothesis that we want to test, that the mean of the alcohol group will be lower than the mean of the control. So minus a half is lower than plus a half. We're going to make this situation just slightly more complicated. So often when you give people dosages of things, you want a group that is drinking something, just not the active ingredient. So in alcohol research, what John Curtin's lab does and lots of other labs do is you basically, you get a glass of Tang. They actually use Tang when they give this to people, and you just rub some vodka around the rim. So it smells like alcohol. It gives people the expectation that they're going to get drunk, but they don't actually get drunk. So you can think of the purpose of this extra group is to test whether expectations create the same kind of effects that you might get with alcohol. Our hypothesis in this situation is pretty similar. So we still expect alcohol to relieve anxiety. And we expect that the mean of the alcohol group will be lower than both the mean of the pure control group and the placebo group. Very similar, just slightly more complicated. So okay, we're faced with the same problem, right, that we were with when we were working with the dichotomous variable. Instead of numbers, which is what worked nicely with the GLM, we've got these text labels: alcohol, placebo, and none. So given the way that we approach the situation where we're working with the dichotomy, and given the hypothesis, do you think that there's a way that we can do something similar to represent this hypothesis with numbers? So just to make sure that you see the hypothesis laid out, our hypothesis is that alcohol will reduce anxiety, placebo and nothing both don't do anything. Anybody have an idea of what numbers we could put up here that might represent this hypothesis?
You could do -1, 0, and positive.
-1, 0, and +1, or is this what you're talking about?
Yeah, or you could set the alcohol to 0 if you just wanted.
So another possibility would be 0, 0.
No. 0, -1, 1. You could just change what you set to 0, just if you wanted your interpretation to be.
So are you saying something like this?
No. 0, -1, 1.
0, -1, 1. So this particular prediction says that the anxiety of the placebo group will be in the middle of the alcoholamine control group. This one says that the placebo group will actually experience lower anxiety than the alcohol group. Does that match our verbal interpretations up here? Well, it could, except that we're predicting up here that placebo is not going to do anything to anxiety.
But then you would want maybe your control to also be doing.
So it would be -1, 0, 0. Any other ideas? I think the hypothesis that most closely matches what we have up here is something like this. So you're assigning the same number that's high to the placebo and the control group, and another number that's lower to the alcohol group. Yeah.
Even if that's your hypothesis, wouldn't you want to like leave room for it to placebo did have an effect on anxiety?
You sure do. We're facing kind of a dilemma, right? A problem. And that's that we have to assign one set of numbers, or we'd like to assign one set of numbers to these three groups, except that any set of numbers that we do kind of misses a pattern that could be happening in the data. For example, this set of numbers right here is missing out on the possibility that there really is a difference between placebo and control. This set of numbers right here is missing out on the possibility that there isn't a difference between the placebo and control. That is an issue. And it's something that we'll come back to very shortly. That's a very important idea. Right now, we'll just focus on this first contrast, but I believe we're coming back to that idea in maybe about 5 slides. It's a very good observation. Okay, I'm going to go with this type of contrast right here that assigns the same number to these two groups and a different number to this group. So we could use this exact contrast, but just as there are certain contrasts that are a little bit nicer to work with when you're working with two groups, there are some numbers that are a little bit nicer to work with when you're working with three groups. So in particular, it's kind of nice if the distance between your two sets of numbers is 1. So for that reason, this is a good contrast because you've made it so that that distance is 1. It's also nice if the contrast is centered. So for a similar reason that you might want to ensure that in a dichotomy situation, you're working with a centered variable, you're working at halfway the distance between 0 and 1. You also might want to make sure that the average of these three numbers is 0. So that's what I'm doing here. This contrast is centered, and it's called, I'm doing something called unit weighting. So unit weighting is that idea that I'm trying to make the distance between the top number and the bottom number to be exactly 1, which makes contrasts easy to interpret. Centering is the idea that the average of the numbers that you're using is 0. These are the same principles that we used. I just didn't use this terminology when we were working with dichotomous variables. Centering, of course, we've done a lot with a lot of different kinds of models. So we're doing the same thing here. And I put these other numbers up here just to illustrate this idea that I could have used other numbers that are statistically equivalent. By that I mean, if you fit your GLM and get your t-statistic, the t-statistic would be the same. They're a little bit harder to interpret. It's harder to interpret that exact coefficient value that you get, but you can use them. Any questions so far?
Could you go back one slide?
Absolutely.
Or your unit weighting, the distance between the smallest and largest values in a contrast is 1. Can you explain that in this example?
So 1/3 minus negative 2/3 is 1.
Okay, I was looking at the one negative 2 over there.
Yeah, so this one right here, this is harder to work with because it's not unit weighted.
Gotcha.
Likewise, this one out here also is not unit weighted. So you could use these, but this one is just a little bit easier to work with, or easier to interpret, I should say. So I'm just going to show you what's happening graphically. So I'm taking the same graph that we started with, where I have labels on the bottom, and I'm going to transform those labels into the contrast values that we're working with. And I'm just making these two things different colors because, well, you'll see on the next slide. So exactly what's happening here is that these two labels, these two groups, are now on the same place in our graph. We're treating them as if they are the same. And this reflects this, well, really assumption that we're making in this kind of contrast that the two groups are equivalent in their effects on anxiety. So now that we've made this change, and we've transformed what used to be text labels into numbers, we can probably go through the same process that we've gone through whenever we've derived a new case of the GLM. So specifically, we can take a line, we can anchor it at 0. That's what we did when we were figuring out how to apply the GLM to a dichotomous case, and then test out a bunch of different slopes of that line. And there's going to be one slope that fits the data the best, where that means that the sum of the squared errors, the sum of the squared function errors, is at its lowest value. We've basically taken a case that used to be a bit more complicated, made it look like something that we've already done in the past. And we can go through that procedure, and there will be a slope that fits the data the best, and that's the slope right here. But to get back to your idea about one of the limitations of this particular coding scheme, we are assuming that these two groups are equivalent. They might not be. And you know, a funny thing about this particular contrast is that if we nudge each of the points in these groups up and down by the same amount. So, for example, if we subtract 10 from each point in this placebo group and add 10 to each point in the control group, and then go through that same process of finding what's the slope that fits the data the best, we'll come up with exactly the same slope. This is something that our coding scheme is missing, is any sort of difference that might exist between the placebo and the control group. And we could subtract and add any number we wanted, and we'd have the same problem. So this is what it looks like if you subtract 20 from the placebo group and add 20 to the control group. We get exactly the same slope. This is what it looks like if we do the same thing with 30. You get exactly the same slope. This is a limitation that we probably want to find some way of addressing. So it seems like we can't just take that one contrast that we've already created. We've got to make some other contrast, some other mechanical variable that sort of takes care of this problem that there might be differences between the placebo and the pure control group that we're missing with our original contrast. So I'm going to call this first contrast that we created C1, contrast 1. This is my convention when I'm working with contrasts. I just give them little names like C1, C2, C3. So can any of you think of a second contrast that might take care of this problem of missing differences between the placebo and the control group? What might be a set of numbers that we can use to capture that difference?
The this first set here, in your alcohol placebo control, so if you do negative 2/3, 0, 2/3.
This one, are you talking
The
about?
first one,
This one right here.
something similar to that.
So the problem that we're facing is that we're comparing the alcohol to the alcohol group to sort of the average of the other two groups. But by averaging the other two groups together, we're sort of assuming that they're the same. And we want to test whether they're not the same, whether there's a difference between those two groups. So do you think that this contrast right here does that?
I think so.
So we're saying that alcohol is low and control is high, but placebo is in the middle. Is that testing whether placebo is different from control? Anybody else have an idea?
Can you leave alcohol out and just test placebo in it?
I think you're on the right direction, yeah. One way to leave alcohol out is to multiply it by 0. Whatever the alcohol mean is, it's not going to have any effects on the total value of it.
So then would it be the second one?
Yeah, that's the second one right here. Do people see why that is? This is, one way to think about this is that these are the numbers that you multiply by the means that produce the maximum value. So there's no other way of ordering these numbers where you get a smaller value. So if, for example, let's say that our means are 3, 2, and 4. So if we multiply these numbers by these and then add up the results, we get a value of 2. But if instead we multiply these numbers by these, we get a result of 1. So we're looking for some way of ordering our numbers such that if there is a difference between the alcohol and the placebo and the control group, we'll get the maximum value that we could by doing this multiplication and adding process. I don't know if that helped at all. Yeah.
I guess what I'm confused about is why you couldn't, like, I see how the second one could work, but I guess I'm confused as to why you couldn't compare the placebo and control in the first column.
So the difference between the placebo and the control is having an impact on the total contrast value. But what's happening in the alcohol group is also having an effect. So
What do you mean by total contrast value?
meaning if I multiply these numbers by these and add up the results, we want to make sure that whatever the result that we get is the biggest value that it can be. That's the contrast that's going to be most sensitive to differences between the placebo and the control group. So yes, you're right that this contrast value is picking up some of this difference, but it's also picking up something that's happening in the alcohol group, and we don't want that.
We're just comparing two conditions.
Yeah, that's another way of thinking about it, is that because we're multiplying the alcohol group by 0, in essence, we're just comparing these two conditions to each other.
So is there a way that you would compare all three of them?
No.
Okay.
No, that's the problem with categorical variables that have more than 3 levels. One way of thinking about why this is the case is that if you're saying that a variable is categorical, you're saying that there's no, before you go into the study, there's no meaningful way of ordering my categories from lowest to highest. So if you're just given these labels, alcohol, placebo, and control, I have no reason to say that alcohol is somehow larger than placebo, which is somehow larger than control. Like, I can't say that. They're categorical variables.
Based on your hypothesis?
Well, your hypothesis is something that you're bringing into it. So based on your hypothesis, yes, and that's what these contrasts represent, is specific ideas about how to compare these groups together. But this is in contrast to a variable like class rank. Because it's a rank, you can say that a class rank of 1 is better than a class rank of 2, which is better than a class rank of 3. You can impose an order on it. But with this variable, alcohol, placebo, and control, there's no meaningful way to say that alcohol is greater than placebo, which is greater than control. Yeah.
I see what you're saying, but so what if your hypothesis was that alcohol produces the lowest amounts of anxiety, and followed by placebo, followed by control?
Yeah, then you might want to use contrast like this. Absolutely. So your contrast is dictated by a hypothesis that you want to test.
So our hypothesis in this scenario to say that we would hypothesize that placebo and control would have different outcomes.
Yeah, so if that's our hypothesis, then
The 0, -1.
yeah, exactly. Like I said, the contrast that you choose is completely dictated by your hypothesis. When you get back to the idea of rank versus categorical variables, having to represent the categorical variable with multiple mechanical variables in your regression is the price that you have to pay for having one less assumption that there's no meaningful order between the variables. So if you want to make that assumption, you've got to represent your categorical variables with a bunch of mechanical variables. Other questions about this?
You just compare placebo and control like a confidence variables. Why do you need to include alcohol if you're not interested in defining it?
Essentially, by giving that a value 0, that's what you're doing. If you're asking, like, why don't you subset the data and look at the subset, basically this is a more powerful test because you have more data that goes into the inner term. I'm going to talk about this a little bit more on Monday and show you that direct comparison. My short answer for now is that this is a more powerful approach.
And the means on the right, those are either arbitrary, correct?
Yeah, this was just meant as a demonstration. These contrasts have an additional property that might not be obvious just from looking at them, and that's that they're uncorrelated. They're orthogonal. They're independent. So one way that you can just verify that they're orthogonal to each other is you take each number, like the 2/3, multiplied by the corresponding value for the second contrast, so 0. Do that for the second one and the third one. If you add them all up, you get 0. That means that they're independent of each other. There's an easier way to do this, which is you just do it in R. You use like core, and you see whether these two vectors, these two contrasts, are correlated, and they're not.
if they were correlated, the outcome would just be the positive or negative.
If they are correlated, you're not doing plain orthogonal contrasts, you're doing something else. There's an approach called dummy coding, which I believe we'll be talking about on Monday, that uses correlated contrasts. That's totally fine, it's just different. Yeah.
But so you should pick numbers that are uncorrelated with each other, that like.
For this approach, yeah.
Yeah.
You're testing one focus hypothesis, and then you've got another sub-hypothesis where you're sort of verifying whether that the assumption that you're making with the first hypothesis is actually correct. Just to give you some additional terminology, this first contrast that represents the thing that I'm most interested in, that's often called a focal contrast. And that second contrast that represents that check on the assumption that you're making, that's often called a residual contrast. A small note here, this is yet another area of statistics where we'll run into lots of different terminology. And sort of as I foreshadowed on the first class, this is also an area where a lot of people have a lot of different kinds of approaches. So this is just one approach with its own specific kinds of terminology. So we've got our variables. We were able to completely represent the means of our different groups. We can now apply the rest of the formal structure of the GLM to test hypotheses about the variable subcat. So first, we've got to choose a model. The variation of the GLM that we're working with is a three-parameter model. We've got two mechanical variables, oscillator stuff. That's our third parameter. We've worked with this model before. This is a familiar model. Next, we have to define null and alternative hypotheses. And to do null hypothesis significance testing, you start from the assumption that the null hypothesis is true. And you fit those null and alternative, those compact and augmented models to figure out the sum of square errors. There are several different null and alternative or sets of null and alternative models that you could be looking at. So for one of them, you might assume that B1, the coefficient for that focal contrast, is 0, and you test whether it's different from 0. We could do the same with B2. That's the residual contrast. That's that check on whether there's something that the focal contrast isn't capturing. We could also test what's called a joint hypothesis. We talked about this briefly last semester. Mainly, I was trying to argue that joint hypotheses are not all that important. I'm going to make the same argument here. So I won't get into that yet, but I just want to forecast for you that this is one of the approaches that you see out there in the literature that I happen to think is not the greatest. I'll give you some reasons why, but obviously you can do what you choose when you're doing your own data analysis. Just a note about this choice of which sets of which null hypothesis and alternative hypothesis you choose is another source of the variation in approaches when dealing with these kinds of categorical variables. Next, you calculate some sort of statistic to formally compare the compact and the augmented models, or the null and the alternative models, using the same statistics that we've been working with since last semester, so FLT. And if you get a sufficient difference, a sufficiently large difference in the sum of the squared errors between the compact and the augmented models, you reject the null hypothesis, otherwise you continue. Using, for example, B. So this is all the same. You can follow exactly the same process as with all the other cases that we've covered previously. So I've included a little bit of our code that I'm seeing is a bit hard to see, but you'll have the reference at least on the slides. And of course, I'll be working with R on Thursday and Friday. So I'm just showing you that the process that you go through to fit this kind of model, it looks fairly similar to other cases that we've looked at. Here, you have to calculate by hand, like add to your data frame, variables that are called C1 and C2. And the way you do that is literally you just say, okay, when you see the alcohol group, give it -1, or sorry, -2/3. If you see one of the other two groups, give it a +1/3. That's what case 1 is doing. It is saying, if this happens, do this. If this other thing happens, do this. If this other thing happens, do something else. Once you've created C1 and C2, you just use LM to put the model, and you get statistics just like with other kinds of models that we looked at. Categorical variables are a little bit special in R, in that R has some special features to deal with them. Actually, in some ways, I think they're more annoying than helpful a lot of the time. But you will, if you're looking at R code on the internet, for example, you will see this alternative approach in that R code. That's using these special variables that R calls factors. I think you've used factors in the past to create graphs. Sometimes they are useful, but sometimes they get in the way. So I'm just showing you on the slide, there are some special functions that work with factors. What's special about factors is that R represents them under the hood as sets of contrasts. And there's ways to access those contrasts, like using the contrast function, to tell R, no, I want you to make C1 be this and C2 be this other thing. Or, basically you tell it how you want it to treat those contrasts. And then instead of adding C1 and C2 to the model, I'm missing one line of code. You can work with treat that factor variable and add it to the model instead of C1 and C2. So what's missing here is fitting M with treat instead of C1 and C2. I'll update that after we're done here. So, yeah, go ahead.
Just as a quick refresher, on your first model, could you briefly explain what that's doing there? Is that your startle as predicted by the first contrast code you have set up for your categories, controlling for the second contrast code?
Right.
And then your output is saying, hey, it's a significant first contrast code that predicts the outcome variable?
We're on, I have several slides that go through the interpretation of these results. Right now, just note that the way the process that you use to fit these in R looks pretty familiar. Yeah, so this is the next set of slides. I'm going to show you some graphs, and we're going to go through exactly what each of these numbers means. So just as a reminder, this is how we're treating C1 and C2. C1 is comparing the alcohol group to the average of placebo versus and nothing. And then C2 is comparing placebo to nothing. This is the final graph that we ended up with. Obviously, this is a little bit different from what you might present in a paper, but it's useful for figuring out interpretations. If you had to guess, where do you think this first number, 61.72, is represented on this graph?
Right in the middle.
Right in the middle. Right here. Absolutely. So this is the intercept. It's where our prediction line crosses the y-intercept. It's the predicted value when all our predictors are 0. In addition, because we've centered our variables, we've centered our contrasts, this intercept has a special interpretation. It is the average of all our 3 means. So just like if you're working with centered variables in a dichotomous case, if you centered all of your contrasts when you have more than 2 levels, that intercept will be the mean of means. That is what the centering gets you, basically.
Is it pulled over further to the right because there's more data points?
Yeah, we have twice the number of data points over here as we have over here, because we're averaging together these 2 groups. Yeah, that's absolutely the case. Just to comment on that a little bit more, essentially we're giving each of these points a little bit less weight than the points over here to compensate for the fact that we have equally sized groups. Okay, so we talked about what C1 is doing. It's basically comparing the alcohol group to the average of the other 2 groups. How do you think C1 might be represented on this graph? Absolutely. So it's the vertical distance that you have to travel if you move over a unit, which is the slope of the blue line. It also turns out that conceptually, because we've done this thing called unit weighting, where we ensure that you're traveling a distance of 1 if you go from the smallest group to the largest group, that this is the difference between the average of this group and the average of both of these groups. And that is true because of that unit weighting. So this last contrast is a little bit hard to see given how I created this graph. but I'll add a little bit of extra information. So you can hardly see it, but I put one horizontal line at the mean of the green points, and another horizontal line at the mean of the red points. So this should be a giveaway, but how do you think C2 might be represented on this graph?
The vertical distance between those lines?
It's the vertical distance between those lines, absolutely. Notice that the way that these quantities are represented on this graph is pretty similar to how they're represented in other kinds of graphs. So we've often looked at slopes of lines, and we've looked at the intercept and distance between two parallel lines. So those same concepts, how these quantities get represented on graphs, and their interpretation is very similar to other cases that we looked at. Because we're working with a categorical variable, we can also think about these statistics as doing operations on means. I've sort of been talking through these as we went through the previous graph. But I just want to make it crystal clear how these values that we get from LM can be represented in terms of means. So the intercept right here, that intercept is the average of these three means. And that, of course, is because of the centering that we did. So this won't always be the case, but it is if you've centered all of the variables. This C1 right here is the difference between the average of these two, so the two groups that got 1/3, and this, so the one group that got -2/3. And again, just to make this crystal clear, this won't always be the case, but because we've unit weighted this contrast variable, it is true. So that's the nice extra bit of interpretability that you get from your unit weighted. And this C2 here is exactly the difference between these two things. And again, that's because of the unit weighting. So these the results that you get from this linear model can be thought of in terms of doing operations on three means. That's essentially what you're doing if you're working in this case where you have a categorical variable with three levels. You create two hypotheses, one focal hypothesis and a sub-hypothesis. Those hypotheses are about means. And when you fit your linear model, you get some results that test whether some differences, basically some fancy difference scores, are different from zero in the population. So we can now go back to this term and orthogonal contrasts and get hopefully a little bit of a better grasp on what it means for something to be planned, orthogonal, and a contrast. The planned bit refers to the fact that you're thinking about some sort of hypothesis that you have about your data, hopefully before you see your data. So you're thinking about, well, do I expect the placebo group to be the same or different as the control group? Or do I expect this sort of linear increase in anxiety? And the reason I say that it ought to be before you see your data is that because this approach is so flexible, you can imagine it would be very easy to fool yourself and like look at the means and say, oh yeah, of course I would expect there to be a linear increase. Or yeah, oh yeah, of course I would expect the placebo and the control groups to be the same. So that's a scenario for this approach, is that you're thinking about this ahead of time and committing to what you think is going to happen before you've seen any data. The contrast bit refers to this idea that you're creating these mechanical variables that represent operations that you're performing underneath. Refers to the fact that you have to represent these categorical variables with one or two levels as multiple mechanical variables. Not just one mechanical variable, but two in the case of a three-category design. And then the orthogonal part of planned orthogonal contrasts refers to the fact that the contrast variables are uncorrelated. They're independent of each other. As I mentioned earlier in the lecture, there are certain types of contrasts that are not orthogonal. But if you're doing this like very sort of a priori hypothesis-driven approach, they ought to be orthogonal. So I've mentioned a couple times that this is an area where there's not necessarily complete consensus about the best way to go about things. So I'll give you an idea of what some of the controversy is. And I have my opinions about this. I have many opinions about statistics, but I'm under no illusions that I'm objectively correct. So I'll just present you with some of the areas of controversy and something about what I think, but it's not to say that I'm objectively correct about this. So with respect to planned orthogonal contrasts, the main area of controversy is what to do with this residual contrast, that secondary hypothesis that I like to think of it as a check on some sort of assumption that you're making about your first contrast. So you can reasonably ask the question, like, should you really care about that residual contrast? Maybe you shouldn't. I mean, if that C1 contrast, like, that basically captures your hypothesis, maybe all you should care about is whether that's different from zero or not. And that's the area of controversy, is how best to handle that residual contrast, or even if it's a thing that's worth thinking about. I think there might be good reasons to care about that residual contrast, but I can imagine research scenarios where you might not, because you don't have a firm idea of how placebo should compare to control. And my recommendation for you is to really think carefully about what it is that you are predicting ahead of time. And really think about, like, can you make a firm commitment about, whatever the residual contrast might be? Because in some cases, maybe you can. Maybe the only thing that you are certain about is that you're predicting the thing that's captured by your primary contrast. I don't think that there's like a one-size-fits-all solution for this problem. So I often find it useful to look at visualizations just like sketch out a graph to when I'm asking myself questions like this. So the question that you might ask is, in the case of this particular hypothesis, so I was saying that we're predicting that the alcohol group will have lower anxiety, and the placebo and the control groups will have higher levels of anxiety. There would be any change. What I'm showing you in this graph is a case where that hypothesis is supported, but there's something wacky happening with that residual contrast. So this graph will have exactly the same C1 value that the other graphs that we've looked at do. But the only thing that I've done is I've added in some non-zero value for C2. Just to show that to you, this is the graph that we ended up with for low, high, high. This is the graph that we're considering. The only thing that's happened is this has gone from high to low. And this has actually gone up a little bit too. So the C1 is exactly the same. If you test it for significance, you'll get an identical value. The only thing that's different is that you have a non-zero C2 in this case. So if you can reasonably say that something like this supports your hypothesis, then maybe you can consider that C2 as like something exploratory, not of primary interest, but you're going to look at it and report it. But if something like this is actually counter to your hypothesis, then maybe you want to say something about C2 as well, not just that C1 is significant, but C2 is small. So small that you shouldn't care about it. There's a methods paper that points out this problem of, among other things, of residual contrasts that have non-zero values. This is this paper right here, Abelson and Prentice. It's a little bit old at this point, so no methodologist has come in and like totally resolved this problem to a point where there's like a great consensus about this. I'm giving it to you as a reference that you can cite as evidence that residual contrasts, maybe you should care about them sometimes. What they recommend is you basically test C1 for significance, test C2 for significance, and they say that you need a significant C1 and a non-significant C2. I don't think that approach is great. What I would recommend is using an equivalence test on C2. So as we talked about last semester, saying that something is non-significant is not the same as saying that it's small, so small that you shouldn't care about it. There's a tool for that, it's an equivalence test. That's a good way of demonstrating that, yeah, C2 really is below the threshold that you consider important for your application. Yeah.
And this assumes that the focal test hypothesis is that the no alcohol and placebo are not different.
That's the running example. On Monday, I'm going to go through at least one example where we're looking at a different kind of contrast. So whatever you're calling a residual contrast, yeah, that's the thing that you want to test. And I suggest that you use an equivalence test. Let me be clear, I can't point to a paper that does this. This is just what I think would be appropriate given my thinking about these problems. I have an ongoing project with one of my colleagues back at UW on this very problem. Maybe someday you can cite a for-sure paper or two as suggesting this method. I think it's a reasonable approach. I think it makes sense, but I don't pretend that I'm objectively correct about this. Okay. So today we talked about this idea of planned orthogonal contrasts. And this is dealing with just one case where you might be interested in categorical variables with more than 2 levels, 3 or more. And specifically, this type of approach works best when you're thinking ahead of time of what you expect, and then capturing those expectations using some sort of contrast, or really a set of contrasts. This isn't the only case where you might be working with categorical variables. It's a common one though, and if you're in a research application where you're dealing with that kind of situation, planned orthogonal contrasts are a great way of approaching it. I think they're really nice. They're incredibly flexible. They can capture almost whatever you can dream of as a pattern that's interesting to theory. I really like planned orthogonal contrasts, but they're not useful for every case. So if you're in more non-planned territory, or you have already looked at your data, or you're working with a bound data set, that was collected by somebody else, this might not be the right approach. In general, when you're working with categorical variables with 3 or more levels, you're going to need to represent those variables using multiple mechanical variables in your GLM. There isn't one contrast that can capture all of what's happening in a group or in a set of groups. Having multiple mechanical variables is basically the price that you pay for making less assumptions about what your variable is. If you want to assume that there's no meaningful ordering between the groups, you have to use multiple mechanical variables to represent it. And this is generally true. So it'll be true for all of the cases that we cover when we're dealing with categorical variables. When you're working with planned orthogonal contrast specifically, you'll have one contrast that represents your primary question. I call that the focal contrast. That's also a term that you'll see in papers. Focal just means primary interest. The extra contrasts that you create are going to be independent of that primary contrast. They're going to be orthogonal, uncorrelated. And you can think of those extra contrasts as capturing things that you might miss with your focal contrast. They're capturing those extra assumptions that you're making when you use your focal contrast. In addition, this isn't a requirement, but it makes your results easier to interpret, I think. It's nice to work with contrasts that are both centered. So the mean across the numbers is 0, and that are unitated. So there's a distance of 1 between the lowest number and the highest number. And whenever you're working with planned orthogonal contrasts, there's this question of what to do with the residual contrasts. One approach that I think makes sense is to do the equivalence test on the residual contrasts. I can imagine some cases where you just maybe you can ignore them. Maybe it doesn't matter what's going on with the residual contrasts where you're that's something for you to think about. Any questions? All right, so On Thursday and Friday, you'll go through how to work with these categorical variables, including this weird thing about factors. On Monday, we still have some content on playing with orthogonal contrasts. Oh, that's right. So the next class, thank you. No class on Monday, thanks. But the next class, we have a bit more content on playing with orthogonal contrasts. We're going to cover cases where you're working with 4 levels or more, as well as other kinds of contrasts. Enjoy your holiday, and I'll see you next.